Section 8.2, Exploring Graphs of Periodic Functions. So we're going to look at the characteristics of a graph of sine and cos. And here we have Carissa and Benjamin creating a spinner. They glued the graph paper onto a board and centered it at the origins. This is x and that's y, and they have this graph here. They turned the pointer counterclockwise, so they went this way through 2 complete turns. They went around twice. Okay, Carissa graphed the distance from the tip of the pointer to the horizontal axis. So she did this distance here. So in other words, that looks like y, and Ben did the x distance. So what we're going to do is we're going to compare their graphs. Okay. Okay, so let's let this graph be Ben. So, and this one be Carissa. So what we're doing is at the point 0, at 0 degrees, how long is x? X is 1 long. That's 0.5, that's 1. So at this point, we're going to do 1. Okay, so let this point be 1. 4 squares. No, we're going to do less than 4 squares. We're going to do 2 squares is 1. 2 squares is 1. Okay. Then when we go to 30 degrees, how far is that x? Well, it's 1, 2, 3, 4, 5, 6, 7, 8, just about 0.9. So at 30, we're just a little bit below. Now, we're going to kind of cheat and go to 45. 45 here is 1, 2, 3, 4, 5, 6, 7. 0.7 is a little more than 0.5. And notice my scale, every 4 is 30 degrees. So 45 is half in between. At 60, I have about 1, 2, 3, 4.5. Okay. And then at 90, you can see that my distance is going to be 0. Okay. My x distance is 0. Now let's look what happens when we go to 120. My distance is now negative because I'm in this direction. So at 120, I'm negative 1, 2, 3, 4, about 0.5. 120, I'm about a negative 0.5. Okay, and 135, that's this point right here. 1, 2, 3, 4, 5, 6, 7, negative 0.7. So notice we're seeing some pretty similar values. At 150, I bet it's 0.9, because remember here I was 0.9. Let's see, 150. I'm at 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so at 150, I'm about -9. And then at 180, you can see that I'm at a -1. Okay, now let's look what happens when we start doing 210. So I'm still in the negative. At 210, I'm 1, 2, 3, 4, 5, 6, 7. Oops, I lost counting. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm at negative 0.9. And at 225, 0.9, I bet this is 0.7. 1, 2, 3, 4, 5, 6, 7. Negative 0.7 is a little more, oops, I should have been a little more up with my 0.9 there. Negative 0.7. 240, I bet I am 0.5. 1, 2, 3, 4, 5. You can see I'm at 0.5. And guess where I'm going to be at 270? 0. Okay? I should have done this in a different color, but you can see that my graph goes down, and then it comes back up. And guess what? As we continue going, it's going to follow that same pattern of going up and down. Okay? Now let's look at Carissa. Carissa's looking at the y values. And I will do this one in red so we can see it a little bit. We're just going to, oops, not move my graph up. Okay, so Carissa, we're looking at the y value. So the y value of this point here at 0 degrees, you can tell that that y value is 0. There's no displacement. So we're going to start at 0. Then at 30 degrees, it's 0.1, we're going right here, 0.1, 2, 3, 4, 5. So 0.5 is right here. Then we could do 45, but we'll skip right to 60. At 60, it's 0.1, 2, 3, 4, 5, 6, 7, 8, just about 0.9. So getting really close to 2. And guess what it is at 90? It is 1 whole unit up. So you can see there's a pattern. When we go to 120, guess what it's going to be? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0.9 units up. At 150, I bet you can guess what it's going to be. It's 0.1, 2, 3, 4, 5 units up, approximately. And at 180, my value is 0. Notice we're still positive because we're looking at positive values of y. Now we're in the negative land of y. So at 210, it's going to be negative 0.5. And then we're going to go to negative 0.9. And then at 270, I'm going to guess it is at 1. And guess what? We're going to follow that same pattern. So we go up to a max of 1 and back down. So what we have to do is we have to compare the characteristics of these graphs, looking at the x and the y. Based on your observations, which characteristics of the graphs of periodic functions are similar to characteristics of the graphs of the polynomial, exponential, and logarithmic? So what's similar? Okay, the polynomial and exponential and periodic functions I have studied all have one y-intercept. This as well has one y-intercept. The polynomial, exponential, and periodic functions all have a domain of real numbers. So that one intercept, we would have continued on our graph here. If we would have, so this would have been, that's y, and that would have been the intercept. And similar here in this graph, this is y, and that intercept would have been there. Okay, so based on your observations, what is different? X-intercept. The polynomial functions I've studied had most 3. Exponential has none. Logarithmic had 1. But periodic have many. So we saw here in terms of intercepts that we have one there, another one there. And guess what? As this graph continues, I'm going to have a number of intercepts. This graph here, I have an intercept, and then I'd come back and have another intercept. So there seems to be more x-intercepts. Okay. As domain, logarithmic functions had a restricted domain. It had to be greater than 0, but all others could be any real numbers. Okay. In this graph, it sure looks like our x value can be anything, right? As we go on, our x's could be anything. It could go in both directions. Now, y values is where we come into play. Okay. Linear and cubic functions both had a range. Exponentials all had restricted, but it looks like these graphs just are between -1 and 1 for the range. The y value is no bigger than 1, and no bigger than 1 and no smaller than -1. And we have a bunch of turning points, which we haven't seen before. Okay, so these kinds of graphs are called periodic functions, a function whose graph repeats in regular intervals or cycles. So that graph, if you kept going around and around the circle, would repeat. There's a couple characteristics called the midline, the amplitude, and the period. The midline is the horizontal line halfway between the maximum and minimum. So here we have a max and min, and that would be the midline. The amplitude is the distance from the midline to either the maximum or the minimum. That's called the amplitude. So in the case of the graph, the very crude graph that we drew, that amplitude is 1 because we said that value was 1. So we went from our midline to our max or a min. Okay, and the period is the length of the interval. So how long it took to go, so you're repeating back to where you started. That's called period. And some of you might notice the word period also occurs in physics. Interesting when you're looking at waves. So in this case, if we went there, the time it took to come back up was 200. Oh, no, it had to go exactly right back up to where it started. So it'd have to come back here. So the period would actually be 360 degrees. Okay. What is the period of each graph? Here they said here is 360. If it's a wave, the period is the interval it takes for the pattern to repeat. So kind of like wavelength in physics, how long it takes to repeat. Okay, so we looked at, these are really the graphs of sine and cos is what we were finding out. So the graph of sine looks like this. So the sine of 0 is 0, the sine of 90 is 1. It's a periodic function. We can see a couple of things. This is in degrees. So you can see that the period is exactly 360, starting here, going there, from where it repeats. They started from the top to the top, 360. Its amplitude is 1. We can also do the same graph, and instead of having degrees, we can have radians. So just remembering that 60 degrees is 1 radian, 90 is about 1.6 radians, so 1.6. So we can scale it so we have radians on the bottom. Okay, so the period is now 2 pi radians instead of, because 360 is 2 pi radians. Your amplitude remains unchanged as 1. Cos is similar to sine, only the cos of 0 is 1. So we start like this. The period is still 360. The amplitude is still 1. And again, we can put this graph where our x values are in radians instead of degrees. So we have the following common characteristics. Multiple x-intercepts. It crosses multiple times. Only one y-intercept, and that y-intercept depends which graph we're talking about. The y-intercept of sine is 0. The y-intercept of cos is 1. A domain of any real number. The range is only between -1 and 1. An amplitude of 1. A period of 360 or 2 pi. And a midline, which is y equals 0. They are congruent curves. So they're actually the same curve. They've just been shifted a little bit. They have in fact been shifted exactly pi over 2, interesting, or 90 degrees. The midlines is the horizontal line halfway between. These two graphs oscillate or repeat, move about this line. The period of the graph is the length of one complete cycle.